we have a comparison theorem that allows us to draw a conclusion about one function based on what we know about another, and it goes like this. Let f and g be continuous functions such that f of x is greater than or equal to g of x for x greater than or equal to a. Before I draw the conclusion, I'm going to draw a diagram. Here we have f, which is larger than g as long as x is bigger than a. If the integral from a to infinity of f of x dx is convergent, then, well, look, let's see what that means. That means that the area under the curve f from a to infinity is finite. And we have g is smaller than f. So the area under g has to be smaller than the area under f. And so if the area under f is finite, then the area under g is finite. So if the integral of f from a to infinity is convergent, then so is the integral from a to infinity of g of x dx. Let me fix this a little bit. There. Now, another conclusion we can draw is that if the integral from a to infinity of g of x dx is divergent, and before I finish writing that, let's go to the picture here. What that's saying is if the area under g is infinite, and if f is bigger than g, then there's no way the area under f is finite. So if the integral from a to infinity of g of x dx is divergent, then so is the integral from a to infinity of f of x dx. In other words, if f is bigger and f is convergent, then what we're saying is smaller than convergent is convergent. On the other hand, if g is smaller and g is divergent, then larger than too big, larger than divergent, is also divergent. People confuse the conclusions you can draw a lot. What if f is bigger and it's divergent? Folks, that tells me absolutely nothing about g. If the bigger one is divergent, I have no idea what the smaller one does. Likewise, if the smaller one is convergent, I have no idea what the bigger one does. For this all to work, the bigger one has to be convergent, and then I can draw the conclusion about the smaller one. Or the smaller one has to be divergent, and then I can draw a conclusion about the bigger one. This isn't going to be a big deal in this particular section, but it will be in a future chapter, and we will revisit this conversation. I mean, I call it a conversation, but here I'm talking to a microphone. Anyway, let's look at an example here. The integral from 1 to infinity of 1 plus the sine squared of x divided by the square root of x dx. The question is this integral convergent or divergent? And I don't have a clue just by looking at it. However, we can note that 1 plus the sine squared of x is greater than or equal to 1 always. Therefore, 1 plus the sine squared of x divided by the square root of x is greater than or equal to 1 over the square root of x, always. If we consider the integral from 1 to infinity of 1 over the square root of x dx, well, that's the same thing as looking at the integral from 1 to infinity of 1 over x to the 1/2 dx. Here we have p is equal to 1/2. We saw in a previous video that the integral of a power function of the type 1 over x to the p is convergent if p is greater than 1 and divergent if p is less than or equal to 1. Here our p is 1/2, therefore this integral is divergent. Since the integral from 1 to infinity of 1 plus the sine squared of x divided by the square root of x dx is larger than the integral from 1 to infinity of 1 over the square root of x dx, or larger than a divergent integral, it follows that the integral from 1 to infinity of 1 plus the sine squared of x over the square root of x dx is divergent.